What we're going to talk about today and also tomorrow are techniques to approximate integrals. We've learned all these techniques to find antiderivatives, and I'm afraid maybe it's my fault, but in the process, what was the purpose to find an antiderivative in the first place? What did it let you find that had like a physical, real meaning? Area under curve, right? So you use this because you say, oh, the area under the curve from a to b of some function f of x is capital F of b minus capital F of a, where capital F is an antiderivative. And often finding an antiderivative is like a big pain in the butt, right? I'll give you all these techniques and you can do all these different things, but unlike taking derivatives, there's no general rules that always work and always give you an antiderivative, and there are actually lots of functions for which you can sort of prove that you can't find an antiderivative of it, like in sort of the traditional format that we think of as finding a function. And so in that case, the best thing you can do is you can estimate the area under the curve. And so the first thing I want to talk about is give me two situations in which it's impossible to find the exact value of a definite integral, and you need to use an approximation technique. So I kind of already gave you number one, which is you need to actually anti-differentiate, right? So one reason would be that you can't anti-differentiate. So for example, like, given integral a to b of little f of x dx, you can't find the antiderivative of little f. And the can't might be that you don't know the proper techniques, but can't might also be that it's actually not possible. Yeah. I mean, for example, this guy, the integral from 0 to 1 e to the x squared. Nothing you know will let you find the antiderivative of that function. Nothing I know will let me find the antiderivative of that function. And I have a lot more math background than you guys do. A major failure is just really, really not possible. Another situation could be maybe you only have real life data. So I have a friend who's an electrical engineer, and he might have like readings from his stuff. Does that make sense? But you might not actually have a function. And it might make sense if you have all of these like points, like maybe this is, I don't know, we'll go to physics. If this is, say, seconds, and this is meters per second, you can measure somebody's speed. You have all these dots, but you don't actually have an equation. Does that make sense? And in that sense, you may also want to estimate. So like when you have discrete data that's only from specific points. Those are two situations that I can think of. Okay. You technically learned how to do a little bit of this when you were in Calc 1, right? So when you first find area under curves, they said, oh, okay, we're going to use boxes, right? Yeah? Okay. And those boxes, you're like, okay, well, I can take this interval, divide it into little pieces, and I can use rectangles because I can do rectangles. Yeah? And your idea was then you sort of approximated those rectangles either using usually the left endpoints or right endpoints of your subintervals. Remember that? Okay. So let's review that really quick. So we want to estimate the area under e to the negative x dx from 0 to 2 using n equals 4 means I want 4 boxes. Does that make sense? And we're going to sketch a graph of the function. So we're going to use the left sum or left endpoints. So first of all, approximately, what does e to the negative x look like? Okay, so someone did that. Yep. Does it look like this, or does it look like this? First one. Yep. That negative inside of the exponent reflects the e to the x graph over the y-axis, right? And what is this one point that stuff goes through? 0, 1. Okay, great. Let me erase the incorrect one and draw that a little bit bigger because my art skills suck really bad if I draw small. No laughing. Okay, you're not laughing. Okay.
Who invented graph paper is a genius.
If I divide 0 to 2 into 4 pieces, how wide is each piece? 1/2. You find that by doing 2 minus 0 over 4, or 1/2. And we're going to make your elementary school teachers groan because we're going to use improper fractions again. So first of all, I divide it in half. I get 1. There's 1/2. What's halfway between 1 and 2? 3/2. My first interval is 0 to 1/2 if I'm using left sums. The estimation technique is you take the height of your box at the left endpoint. So there's your first box. Second box, what would you plug into your function? 1/2, yep. Third box, you'd plug in 1. Fourth box, you plug in 3/2. So here's the notation I'd like you to use. When we do a left sum, let's use an L, and let's give it a subscript of how many pieces. Is that like L sub 4? I think your textbook did that back when you did this in Calc 1. Okay, what's the area of the first box? What's its width? 1/2. What's its height? Yes, and that you got by taking e to the negative 0. Does that make sense? Okay. The next box, what's its width? Times its height is e to the negative 1/2, because when you plug it in, there's the negative sign there. Does that make sense? Okay, next box is width is 1/2. Its height is e to the negative 1. And lastly, we have 1/2 e to the negative 3/2.
So is e to the negative 0 just e to the 0?
Oh, yeah, which is 1. Yeah, I just did want to point out that what you do is you plug 0 into the function. Does that make sense? Is there anything you can do to make your life a teensy bit easier here?
Factor out with that?
Factor out 1/2. So it's 1/2 times 1 minus, or no, plus, excuse me, e to the negative 1/2 plus e to the negative 1 plus e to the negative 3/2. On your take-home quizzes, because you have access to technology, like I want you to actually use it. Does that make sense? If it was a question on a test, we'd have you leave your answer like that, it's good enough. But since you have a calculator, you should actually get me a decimal approximation of this with your calculator, okay? It is about 1.099. And this is just an old habit of mine. The AP test always required 3 places of accuracy. I also, let's just do 3. Unless I specify otherwise, okay? Just to make it consistent.
Wait, so does this mean if the answer is like ln of 8, you actually want us to calculate?
I want you to give us both. Yep.
Okay.
Yeah. So if the answer is ln of 8, give us both ln of 8 and give us this. So give us both the approximation and, I mean, ln of 8 is no less exact than this thing. This just happens to be 3 things
Right.
added instead of 1, right? So I'd like both answers, both the exact and the approximation. But if it was a test, then, of course, like, you know, you leave it as is because you can't use calculators. Okay.
Do you want that for everyone, or one that's just like that?
Like pi 8 plus 1/4, like.
Do you want us to?
Can I plead the fifth and go back and look at what I did my take-home quiz? I think in general I'd like it for everything. Okay? If your answer is 1/2, that's fine, right? But in general, if it's like pi over whatever, I think I'd like approximation of that as well.
Okay.
Okay. Now, so there's the left sum. Now the directions also say to compute the error for both estimates. So how do you do that? How would you find the error? Like this is an estimate of the error in the curve, and it's not exactly what it is, right? So to find the error, does it make sense that that's going to be the actual minus your estimate? And being able to do that does depend on the fact that you can actually find the actual area, which you can do in this one. Does that make sense? On lots of others where you're asked to estimate, you can't. But on this one, you can actually find the area exactly.
But if you can find the actual area, then what's the point in estimating?
Well, the point for this one, it's a good question. The point with this one is to point out how accurate the estimate is. Does that make sense? And then we'll have different techniques to estimate the error when we cannot actually find the actual antiderivative. A lot of actuals, sorry. So how do you find the exact area? You integrate from 0 to 2, e to the negative x dx. Can you find an antiderivative of e to the negative x? What is it? Minus e to the minus x. Okay, so that's negative e to the negative 2 minus negative e to the negative 0, which I believe is 1 minus 1 over e squared. Do you guys agree with that?
Don't you still have to find like an approximation of that in order to actually do math it though?
If you're asked to find an approximation, you have to find the approximation. But on some questions, we're going to ask you to find the approximation and also figure out how close it is, as in find this thing called the error.
But you like, that's incompatible math there.
Later.
They're trying to find the error.
To find the, okay, moving on. To find the error, you have to, like to find the error exactly, you have to know what the actual value is.
Yeah.
Yeah? Okay, which is what I found. Yeah?
Yeah.
Okay. So,
Just subtract the estimate.
yeah, so the error is equal to 1 minus 1 over e squared minus your left estimate, 1.099.
Can we just leave it at that?
Nope, you can't. You have to actually punch buttons, 0.234.
And with that all
It's so fun, it's kind of funny, you're like, I want to use my calculator. No, I don't want to use my calculator. Okay, what, yes?
So is that an approximation for the error too then?
No, that is the exact error. I mean, it's an approximation in so much as this number that I used was an estimate. Does that make sense? Like, this is an estimate.
No, I get that's an estimate. I mean, like, if you get that answer off your calculator, is that like the full number, or is the calculator rounded or something?
Yes. She said only 3 decimal places.
I don't understand your question.
He's talking about sig figs.
Hmm?
I think he's talking about sig figs. So how I see it.
Yeah, but in the end, it's probably rounding somewhere if it goes off the end of the calculator.
Yeah, so it's not it's definitely not an exact error because this thing that we use is rounded. It's not precise, but this is the real error, how much you're off by, as opposed to what we'll do later, which is find estimations of how much you're off by. This is only an estimation because this is a rounded number. Other than that, it's not really an estimation. Okay, I think that's the best answer I have right now. Okay, how about the right side? So same picture, well, similar starting picture.
Wait, why was the error negative if it was an overestimation? An overestimate.
Good question. Let me pause for a sec. Okay, it's okay, later. Okay. All right, so right estimate. Plug in a half, a 1, a 3/2, and a 2. Can I factor out that 1/2 right off the bat with this guy? Yeah, so 1/2. What's my first thing I plug into E? And then e to the -1. Next comes e to the -3/2, and lastly is e to the -2. And that's approximately 0.666.
That's a very large difference.
It is a really big difference, yes. And the error, as your book describes it, as they define it, will be 1 minus 1 over e squared. The exact thing is not different from last time, right? That didn't change. Minus this 0.666,
So
which
what's the
is,
devil's number?
well, the devil's number I think is in decimal. Zero 0.197. If you look at the absolute values, this one actually is closer to the actual area than the other one, isn't it? Yeah. And I think what this does is it just tells you how much to add to your estimate to get the actual area. Whereas the other one says how much to take away from your estimate to get to the actual area. Yeah.
So isn't it always, like, that's how much you always add to it?
It's definitely not an always. It's specific to the case, the fact that we used 4 points. So it's definitely, there's no always here. But the only always that exists here is that the way that your book defines error is equal to actual minus your estimate. That's the order they're always going to have things in. That's always true. I think you also, a far more accurate way to measure things or to estimate things is to use something called the midpoint rule, which you should have learned a little bit about in Calc 1. So the idea here is that you start the same way, you divide your interval, this one also into 4 pieces. But instead of plugging in left points or right points, you find the middle point of each interval and you plug that in. So what's midway between 0 and a half? Quarter. And how about a half and 1? 3/4. Next one, see the pattern is going to be 5/4. Do you buy that? And the last one's going to be 7/4, right? And I just can't draw straight lines if I don't. So the idea is you go up to that middle point on your graph. And what does this estimate kind of do every time you make a box? It has a little above and a little below, so it kind of, the amount you overestimate by kind of seems to cancel out the parts you underestimate by, right? Not perfectly, definitely not perfectly, but it's better. And one thing that this, when we compute the error estimate for this guy, will show is that this guy's way more accurate than the other 2 methods. So this one, we'll say M for midpoint. Did the widths of the boxes change? No, they're still a half. What's height of first box? E to the negative 1/4, yep. Height of next box? Great, e to the negative 3/4, and then you get the idea, e to the negative 5/4, e to the negative 7/4. And that's approximately 0.856.
That's not the average of the previous 2, right?
It is not the average of the previous 2. The average of the previous 2 is something called the trapezoid rule, which is the next thing I'm going to talk about.
Is that one even more accurate?
Not really. Okay. You guys are kind of whiny today. So just to distinguish between the errors of different things, let's call them like E sub M for error midpoint. Does that make sense? The first one in example 1 should have been E sub L. Next one, E sub R. Does that make sense?
Yeah.
Okay. So E sub M will be the actual minus the estimate, or 1 minus 1 over E squared minus 0.856, which is so much better. It's approximately 0.009. Is anybody slightly amazed by that?
Yeah, that's a very small percentage.
It's a very, very, very small bit. And the other thing that's kind of cool is it's a very, very, very small bit, just 4 pieces. Think about what if you did like 10, which wouldn't even be all that hard with a calculator, right? And I think that your error gets small really, really quick. This is a really, really great, accurate method for estimating areas under curves.
I just know that if I use 10 boxes, my error would go up because I made a mistake in my math.
That's not the error in your estimate, though. That's like, an operator error. Those are different kinds of errors. So I think one of the first things you think about when you see these methods is you get this left sum, you get this right sum, you think, oh my gosh, I should just average these 2 things, right? And because that'll make it better, yes? And it will, and that actually ends up being something called the trapezoid rule.
Better than midpoint.
It actually is not better than the midpoint rule. The midpoint rule still wins. Okay, so the idea behind the trapezoid rule is to take your subintervals and take the two endpoints and connect them with a straight line. Does that idea make sense? Instead of just saying, okay, I'm gonna go from the left endpoint over, or right endpoint over, or the middle point over, I'm just gonna take those things and I'm gonna connect them with a straight line. Can you find the area of such a thing? Technically, yeah. I think the area of a trapezoid, I'm sure you all knew this at one point in time in your lives, is 1/2 base 1 plus base 2 times height. Have you seen that before? It's just that this one's kind of on its side. Like the height is this, right, from x0 to x1. And then base 1 is this line, base 2 is that line. Okay. So let's do that just for this guy, and you're going to see where that pattern's coming from. Okay, so first of all, first box.
This is quicker than cutting it up into a rectangle and a triangle and doing.
This will have a nice relationship to left and right sums that you can then use, okay? So just let me get there. So for the first box, we have the 1/2. What is base 1? Like, you took x0 and what'd you do to it? You evaluated it. Yep, you put it into f. Does that make sense? You plug in x0 to get this thing, right? What do you do to get this next base? Plug in x1. And then the height is this distance, which is, in this case, it's delta x, right? It's like which in our previous one was what? A half, right? Okay, that's the first box. Okay, what about the second box? So this guy. What is this first f of x1? Yep. And plus f of x2, and then once again, its height is still delta x, right? The next one's going to be 1/2. It'd be f of x2 and f of x3. Do you buy that? Times delta x. And how about the last box? F of x3, and then what else? F of x4, and still times delta x, right? Yeah.
If you have a negative slope on that portion, would delta x then be negative?
Nope. Delta x is the distance from here to here. So nope, the negative slope doesn't come in at all. That you're thinking of the derivative, which is something different, probably. So is there any obvious greatest common factor? 1/2 and delta x. So in this case, T4 is delta x over 2. And then think about the stuff left behind. How many f of x naughts are there? 1. How many f of x 1s? 2. How many f of x 2s? 2. How many f of x 3s? 2. And how many f of x 4s? Do you see how they have that formula up here? It's the same thing, except for it's just more general. We just did 4 pieces, right? So one difference with this versus the left sum, right sums thing is that in this one you actually use all the points, right? Like for the left sums, you just use the first 4, right sums, it was the last 4, right? Midpoints were all different. But for this one, you use them all. Does anybody see how this relates to the left and right sums?
Put in your f of 0, be like your left sum, and your f of 4 would be your original right sum.
Kind of, yeah. It's the average of the two. So if I did that left sum for that picture, it would have been delta x, and you would have done f of x naught plus f of x1 plus f of x2 plus f of x3, right? The right sum would have been delta x times, what would my first point have been? F of x1 plus f of x2 plus f of x3 plus f of x4, right? When you average them, see what you get? You get that L4 plus R4 is equal to delta x times a singular f of x naught, 2 of all the middle guys, right? Plus the last guy. And then what do you have to do to do the whole averaging business? You have to, that's where the over 2 comes from. Okay? So you can either do one of two things. You can use this formula to find the, like, trapezoid rule estimate, or you can use the left sum and the right sum. And what you will do depends on the context. If I ask you to find the left and right sums, by all means average them, right? But if I don't, probably better to use this off the bat. Does that make sense?
Because you just plug it into a calculator.
Because you can just plug in your calculator to plug, this will be plugging in less things because you're doubling all the stuff you've got to double. Does that make sense?
Yeah.
Okay. Oh, man. Okay. Trapezoid rule and midpoint rule with this guy. And I'm out of time, so I'm going to wait and do this one next time. The last thing that we did was we found the formula for the trapezoid rule, which really is the average of the left and right sums, correct? So if you're asked to find left and right sums and find the trapezoid rule, then go ahead and just use that. But if you're asked to do the trapezoid rule and that's all you're asked to do, then you probably should just use the formula. Does that make sense? Okay. So we're going to use the trapezoid rule and the midpoint rule with n equals 5 to approximate this integral. And I purposefully chose one that we could actually evaluate exactly so we could compare it to, compare the two methods and see which one is more accurate. Does that make sense? Okay. So how about, since we're going to compute the errors, let's start by getting the exact. So integral from 1 to 2, 1 over x dx. What's the antiderivative there? ln absolute value of x, but officially 1 and 2 are both positive, so it probably could be sloppy. So that's natural log 2 minus natural log 1. What is natural log of 1?
0.
0. So this is equal to
Natural log of 2.
natural log of 2. Yeah, so that's the exact area under the curve. Okay.
And then can we use the midpoint because it uses less base?
Say that again?
Can we start with the midpoint after that because it uses less base?
I'm just going to do trapezoid first. I asked for it first, but it doesn't matter. So when we're going to, for both the trapezoid rule and the midpoint rule, we need to figure out what the width of each interval is, right? So delta x is 2 minus 1 over 5, which is 1/5, or as a decimal, because that might actually be easier in this case. What's 1/5 as a decimal? 0.2. Okay. So trapezoid rule with 5 pieces. So the first thing with the trapezoid rule is you kind of have to remember that you're doing an average. So instead of just delta x, it's delta x over 2. Does that make sense? So 0.2 over 2, which you could, of course, just say was 0.1. Okay, and I'm just going to let f of x equal 1 over x, and let's just say what we're going to plug in. So what's the first thing we're going to plug in? 1. And we're only going to do that once, right? That would have come from the left sum in your averaging process. Plus 2 of whatever the next thing you plug in, which is, let's just give me a decimal, because you have 1.2. Does that make sense? Which is 6/5.
But you gotta reverse it because it's 1 over 6.
Oh, you're right. I'm just saying what we're plugging in. You're saying what you get once you plug it in. Does that make sense? So yeah, we're both right. You're just we're just phrasing differently. Next, you'll plug in 1.4, 1.6, 1.8, and then when you plug in 2, as in your right endpoint, does that have a 2 in front of the? No, it's just f of 2. Okay, so that's 0.1 times 1 plus 2 over 1.2, 2 over 1.4, 2 over 1.6, 2 over 1.8, and I think also, well, 1 over 2 in the last one. Do you guys agree with that? Or if you had, fractions, they would reciprocate, just like you were saying. So that's approximately equal to 0.696. Need to remember the right way to do it. Let's just compute the error right away. So the error for the trapezoid rule, we think that this book defines it as the actual minus the estimate. That's what we did yesterday, right? So that's ln2 minus 0.696, which I believe comes out to be negative 0.003. Did you guys get that? You had a calculator check?
Yep.
Okay, great. Kind of amazing, right? That's not so bad, right? Just 5 pieces and you're pretty close. Okay, let's find the midpoint. So with the midpoint, do we have to do the 0.2 over 2? Nope, just 0.2, because in this case, remember, trapezoid kind of came from averaging, that's hence the division by 2 business. And then you can kind of look at the work that we did to kind of get the midpoints. The first subinterval is from 1 to 1.2, right? What's the midpoint there? 1.1. And then f of next would be 1.3, yep. 1.5, right? F of 1.7, and lastly f of 1.9.
Is this gonna be even closer?
It's even more accurate, yeah. This is, I trust you guys can all write this as 1 over 1 plus 0.1, you guys can all do that, right? So when you plug this into a calculator, you get approximately 0.692. So the error in this case, so it's the actual minus the estimate. So ln2 minus 0.692, which is 0.001.
It's like 3 times more accurate.
Yeah, I think on average, we'll learn some estimation formulas for errors today, and I think that in general, I think it's twice as accurate, even though it could be even more. Okay. Yeah, the point is that the midpoint estimation technique is a really, really, really good one. So that's the main point.
It's really good and it doesn't take as much writing.
Well, there's that too. Which also in that case would be like less programming, right? Because you plug less things in. Yeah. Okay. So
Is this always the case? Is the midpoint rule always the best one?
next slide.
Okay.
Okay, yep. There is a better rule, it's called Simpson's rule, we'll learn about that one today as well, okay, but midpoint's pretty good. So these are things that you did not learn in Calculus 1. So, and I'm not going to try to explain to you where they come from, I want you to know how to use them, okay? So you suppose that your second derivative is less than or equal to some number k for all the x's on the interval that you're looking at. And so usually you're going to have to find this number. And what it will be depends on the situation, like what your function is. And if we ask for this on a test, we're going to give you the second derivative so that you don't make a mistake taking the second derivative. Does that make sense? And then if E sub t and E sub m are the errors in these trapezoid and midpoint rules, the absolute value of the error in the trapezoid rule is less than this expression. And the absolute value of the error in the midpoint rule is less than this expression. So
Literally twice as easy.
yeah, look how this denominator is twice as big as the other one, right? Which means that in general, the midpoint rule is twice as accurate as that trapezoid rule. And your accuracy depends on a few things. It depends on how big your interval is. Does that idea make sense? Because big interval, if you have like just 5 pieces, well then you're going to be a lot less accurate, right? So the b minus a is accounting for the width of the interval. The second derivative accounts for how steep, the concavity of the function, which kind of also talks a little about the steepness. And then the n, how many things number of pieces you take also matters. So the only work that is different from situation to situation is figuring out what the k bound is. And that will be different in different cases. So we'll go through a few of those, okay? So, and those estimation things that we have, they let us figure out, so I want this kind of accuracy, how many pieces should I use? Does that idea make sense? As in, I know I want it within this close, and what should my n be in that case? And you can figure that out. Yes?
Okay, so since it's asking for both of them, but you know that the E sub m should roughly be about twice as accurate as the trapezoid, could you just figure out the trapezoid's accuracy and then assume midpoint's even better?
Let's do it, and then you can see if your argument generalizes, okay?
Okay.
Okay. So how large should we take n in order to guarantee that the trapezoid and midpoint approximations for this integral are accurate to within 0.30 and a 1? So the first thing, to use both of those formulas, we have to find this k thing. And we have that the second derivative of x is less than or equal to some number k. So we need to look at the second derivative. So look at f prime prime on the interval from 1 to 2 and figure out where is f prime prime's absolute value biggest on that interval. And that gave you an easy function. So f of x is x to the negative 1. What's the first derivative?
Negative x to the negative 2,
Great, negative x to the negative 2. What's the second derivative?
2x to the negative 3,
Do you guys agree with that?
4.
I think it's 2, yeah, okay. Which is the same thing as 2 over x cubed, right? Did you buy that?
Yep.
Okay. So that's your first step, is to get the second derivative. Second step, we're going to find this k value. So for this problem, what is the interval we're looking at? So we have 1 to 2. Look at the absolute value of the second derivative, which in this case is just 2/3, 2 over x to the third. Do you guys agree with that? Do I really need the absolute value bars there? Not for the interval that I'm given. Does that make sense? Like if the interval included some negatives, then I would, but since the interval that I'm given is positives, you could be lazy and drop them. Now think about what 2 over x cubed looks like approximately. I think if I draw it so it's your perspective, like there's this, and then it kind of does this decreasing thing over here, right? Like roughly speaking, that's what 2 over x cubed looks like. This and then this, it's an odd function, right? So at which point in the interval from 1 to 2 is it going to be biggest? 1. So this is largest at x equals 1. Fancy math word. Thus, f prime prime of x less than or equal to 2. That's going to be our k. If you're given a more complicated function, a really reasonable thing to do is to graph it, like using something like Wolfram Alpha or a calculator to get a graph of it, and look for, then take its absolute value and look for where is it the biggest. Does that idea make sense?
Are you gonna let us use a calculator on the test?
No, in that case, I'll talk about how we're going to do it on the test, which will be a little bit different. But for your take-home quiz, part of the point is you should also use a little bit of technology for some of this stuff. Not for everything, but for some of it. Okay. So let's just look at E of t. So we have the absolute value of E sub t less than or equal to, so plug in the stuff. What goes in for our k? 2. What goes in for B and what goes in for A? In for B goes 2. In for A goes 1. So 2 minus 1, and that to the third is part of the error formula that you're given, right? Over 12, and do we know how many pieces? No, so that stays a variable. So we're trying to find. So far, we okay? Also, one more thing, you do not need to memorize these error formulas. If they're on the test, we will give them to you. Okay? So don't waste your time. So you want this to be less than 0.1231. Did I miscount again? No, that's good. Okay. Does that make sense? You know your error is less than this, and you want that to be less than that, which will be like more than you need.
Can you solve it out?
And you can solve it out, yeah. So like, for example, ignore the E sub t thing for now. Couldn't you multiply the 12n squared over? Uh-huh. So we have, steps were done differently than me. So I have 2 is less than, what's 12 times point, lots of zeros and a 1. 0, 0, 1, 2, right? Is that the same? Did I do it right? Because I'm nervous. Yeah, okay. And then what would you do next? Divide by 0.0012. So we have, and when you do that, you get 1,666 point, probably 6 repeating, so we'll just say 7. And then you root, yeah. And we have approximately 40.8 is less than n. So you need your n to be bigger than 40.8, and n is the number of pieces you pick. So n has to be a whole number. Does that make sense? Officially, n has to also always round up. Like if this was 40.1, 40 wouldn't be accurate enough. Does that make sense? So the n for the trapezoid rule, n must be bigger than or equal to 41. So for your final answer, I want the whole number. So that I get that you understand that this is like a thing where I can't do halves or 8/10, right? Does that make sense?
I'm just thinking 41 integrals would be a nightmare to solve.
It would be, but if you have mad computer programming skills, or even basic computer programming skills, this is probably not a very hard thing to put into a computer to do, is it? No.
I'm not familiar with C++.
Okay. Learn MATLAB, is that what you said? Yeah. So for the midpoint rule, what's different? What changes?
12 changes to 24.
Yep, the 12 becomes 24. So 2 times 2 minus 1 to the third over 24n squared less than 0.0001. So we have 2 is less than 0.0024 n squared. My notes skipped a step. Don't like it when they do that. So when I divide by 0.0024, I have that 833.3 is less than n squared. When I square root, I get 28.9 is less than n. So n must be bigger than or equal to what whole number? 29. So it is not true. One thing that is not true is that the relationship between the number of pieces isn't half. Does that make sense? What that whole 24 and 12 relationship means is that given the same n, on average, in general, the midpoint will be twice as accurate as the other. But that doesn't tell you that the ends will be twice as much as the other. Yeah.
Okay. What I was more saying is like, if it asked you to like get them within that accuracy, but it didn't need you to like get them bare minimum within that accuracy, couldn't you just find what makes the trapezoid rule that accurate? And then
Oh,
do
yeah,
both
yeah,
of
yeah,
them?
yeah. I think what you're saying is that couldn't you figure out what the trapezoid rule needs and then use the same thing for the midpoint rule because you know the midpoint rule is more accurate?
Yeah.
In general, yes, but I think that depends on the situation. And in some situations, you care a lot about how much computational time you spend doing something, and so you wouldn't want to do something that was overkill. It also isn't what the question is asking. So I get your point. I get your point. Yeah, this specific question, I get your point, but I think that the point is to be as efficient as possible.
So you could just guess and check with different numbers of divisions until you get to the right one,
Yeah, but that would be really inefficient.
and yeah, would.
Okay, moving on. So, there you go. So use the midpoint rule with n equals 10 to approximate this integral. So in this case, I'm not going to actually make you list out all 10 things. I'm going to show you my shortcut notation for notating that you get that there's a pattern, and I'm going to just put it in my calculator now. So first of all, what's delta x? So 2 minus 0 over 10, which is 0.1/5 or 0.2. Okay, and midpoint rule 10. So it'll be 0.2 times, what's the first thing we plug in? Do you guys have questions? Okay. So you've got 0 and you've got 0.2, what's halfway?
0.1.
0.1. So e to the negative 0.1 squared, right? Or f of 0.1. Next, you're going to plug in e to the negative 0.3 squared. Does that make sense? And here's the pattern thing, plus dot, dot, dot. And then just give me like the last two. So you're going over to 2. What's the last thing you plug in? So that'd be 1.8, 1.9, right? So the last thing you plug in is e to the negative 1.9 squared, and the second to last thing is. Is that negative getting squared?
How the way you wrote it.
Nope, and it's not supposed to be either, right? Okay, yeah, so not the way I wrote it, and it's not supposed to be. Does that make sense? Because otherwise, I mean, that you have to have some way for a square to remain negative, right? And this means first you square x, then you make it negative. That's what that is officially PEMDAS, right, or operations. Okay, so when you calculator, it's approximately 0.882. That. Okay. So what I want to talk about here is how could you estimate k with or without technology? So how to estimate k with, and that's what we would expect on your take-home quiz. So I should say the first thing you do is you should graph f prime prime of x. What would be on what interval? On 0 to 2. And you're officially looking at the absolute value of it, so you're looking for either the highest point or the lowest point. Does that make sense? And looking at which number, once you absolute value it, gives you the bigger of the two. Does that make sense? When you do this, you get that f prime prime runs from y equals -2 and then up to about 0.9. So it looks something like this approximately. So there's -2 and it goes upsy downy type thing, and this top value, even though my scale is sucky, is about 0.9. So the absolute value of the second derivative is less than or equal to, what would you take in this case? When you absolute value it, what, like if you absolute value this part of the function, it flips it up, right? So it takes that negative 2 and makes it into a positive 2, so this is going to be less than or equal to 2. So in that case, e sub m is less than or equal to 2 times 2 minus 0 to the third over 24 times, that was n squared, right? And our n was 10, right? Does that make sense? So I think you guys can all push enough buttons to figure out what decimal that is, right? I don't have it written on my notes, but you can do that. So here's what I say for without. So second derivative equal to absolute value e to the negative x squared times 4x squared minus 2. Okay. So e to the negative x squared is positive, so absolute value bars are not necessary there, right? Is 4x squared minus 2 always positive? I don't think so. As it's a parabola and then it's shifted down 2, right? So it's not always positive. I'm just going to keep it in absolute value bars.
Well, it's shifted down 2, but the parabola's also multiplied by 4, so you assume that even if you
put in 1/2.
you have to look at roots
So
of
we raise
numbers.
the x equals 0, just plug it up.
Yeah, you can play. So anyway, I'm just going to be uber conservative, okay? Like, I think it's okay to be really, really careful. So I think worse anyway. So you could actually, I mean, this 4x squared minus 2, I mean, you could actually graph, right? So when is it 0? The lowest it goes is negative 2, right? When is it 0? Not a nice number, right? Isn't it root 2 over 2? So 4x squared minus 2 is equal to 0 if 4x squared equals 2, x squared is 1/2. So those that point's 1 over root 2, or x equals, that's all the same thing as root 2 over 2, which is about 0.7. Yeah. What's our interval? 0 to 2, right? Well, here's what I would do. Let's do this. This is less than or equal to e to the negative x squared times 4x squared plus 2. That's certainly true, right? You buy that? Just don't worry about that negative because we're just going to get a general bound. So think about, when is this thing biggest on the interval from 0 to 2? It has a negative exponent, right? So as x gets bigger, that's going to decay, isn't it? So that's biggest at x equals 0, right? Oh, this is harder than I wanted it to be. E to the 0. When's this part biggest? At 2. So let's just make it uber conservative and say, okay, well, 4 times 4 plus 2. So certainly a good bound, or a very bad overestimate is 18.
It's like so conservative, you can almost see the flag pin on his adult diaper.
Yeah, it's so and then all you do is you change this into an 18. So the point is just make some kind of arguments with inequalities, like this would, then this also really isn't even possible, right? Because you can't plug 0 into one part and 2 in the other, right? Yeah.
If I turn the 4x squared to plus 2.
I can do that because it's an inequality, can't I? Like, this is certainly a true statement. Does that make sense? That is definitely not true if those things are equal. As in, absolute value bars don't change those minuses into pluses. That's totally not true. But worst case scenario, you could just say, oh, well, this is certainly a true statement, and then I get an always positive stuff. So it's just a way to get a good, not a good, but a really conservative estimate. You could also probably argue something about how you could figure out that maybe 2 is also okay in this case, but I think it's more tricky than I want to go into. Okay. So that's kind of it for those error bounds. let's also talk about another method. It's this one called Simpson's rule. Yep.
Are they trying to be clever there, or was there actually a guy named Simpson who figured this out?
I'm pretty sure there was a guy named Simpson.
Yeah.
And the Simpsons, now, what might have been clever there is the Simpsons would have been named after this guy, because the Simpsons, if you know math, are incredibly geeky. There's tons of stuff in there that's like really geeky math. So when we did the trapezoid rule, the basic idea was to take those two endpoints and connect them with a straight line, right? And that was an approximation. What we do with Simpson's rule is you estimate with parabolas, as in you take 3 points, and maybe your evil Algebra 2 teacher, because I know I was one of those teachers, gave you 3 points and said, find the parabola that goes through these 3 points. It involves a system of equations, and it's pretty tedious. So given 3 points, you can find a parabola, just like given 2 points, you can find a line. And then parabolas are things that are actually pretty easy to integrate. Does that make sense? So you can find the area under the first parabola, plus the area under the second parabola, plus the area under the third parabola. And you do this derivation, and it's kind of gross, and what comes out is this expression. There's this predictable pattern to the coefficients. And one consequence here is that n must be even. And that's something that pops up when you do the derivation. So a couple of things to observe. The delta x is divided by 3. That's just what happens when you do these parabolas, and then you do the integrals of areas under parabolas. And there's this pattern in the coefficients. You know how you have one of the first, one of the last. And then what happens with the middle ones, they flip-flop. There's 4, and then 2 of the next one, and then 4. And it always begins on 4 and ends on 4. And it goes 1, 4, 2, etc., ends on a 4, and ends on a 1. That's the pattern of those coefficients.
So it's alternating between two.
Alternates 4, 2 in the middle, beginning with 4 and ending with 4.
It doesn't end on one.
Well, officially ends on 1, I guess. Yeah, it ends on 1. But of the intermediary things, the pattern starts with 4 and ends with 4, okay? And in some sense, it's a little bit similar to the trapezoid rule in that you use all the points. Does that make sense as well? Unlike where the left estimate left off a point and the right estimate left off a point, right? Okay, so let's do one. Let's use Simpson's rule with n equals 10. This isn't what you guys have, is it? No. You guys have integral from 0 to 1 of e to the x squared, right? Yeah.
And it is equal to 4.
Yep. Which is much more humane, right?
Yes.
Okay. So delta x is equal to?
0.25.
Yep. 1 minus 0 over 4, or 0.25. Okay. So S4. So that will be delta x over 3, so 0.25 over 3. And what's the first thing you plug into your function, where f of x is e to the negative x, e to the x squared? First thing is you plug in 0, yep. The next thing you do is you do 4 of plugging in what number? 0.25. Next you do 2 of e to the 0.5 squared, 4 of e to the squared, and then finally e to the 1. And that ends up being approximately 1.463. I want to do a quick, just really quick fraction review. 0.25 over 3. I could have also written that as a quarter over 3. Yes, you agree? Okay, so many of my students get this wrong that I need to explain to you what it's supposed to be. So you have all heard that division by a fraction is multiplication by a reciprocal, yes? Okay, so which one of those fractions is the one that becomes reciprocated? The 3. This is the same thing as a quarter times a third, which is a 12th. I mean, the reason that that's true, this is just really basic. You say, okay, multiply that by 1/3, this by 1/3, the denominator cancels, that's why the bottom is the one that flips, right? So, but so many students, if I give them a quarter over 3, they say something crazy like it's 3/4. So just, there you go. Okay, FYI.
Don't the 3's cancel each other out? If you're doing that problem?
Like this, like right there? That one?
But you see, it's 0.25 over 3 and 1/4 over 3, so the 3's could go away.
0.25 over 3 equals
1/4 over 3. So the 3's could go away.
Yeah, that would still be a true statement, but the point is not. The point is figuring out what is 1/4 over 3 as a fraction.
Oh.
Does that make sense? That it's okay. That was what my point was. Okay. So far everything we've done has been like a function, right? So let's do things that are not functions but are given in different ways, like as graphs or tables. Like this might be something that happens to you like in life where you have something and you have data and you have to estimate the area under the curve. So imagine, just think to yourself what the area under this curve represents. So you have your t-axis is in seconds and your velocity axis is in meters per second. And you start at 0 and then the velocity like levels off at 10-ish. What is the area under the curve telling you? The distance, how many meters were traveled by this person, right? Okay. So we're going to use a Simpson's rule to estimate the distance the runner covered during those first 5 seconds. So from your table, can you deduce what your delta x is?
I really got really slow really fast.
0.5. I have no concept of what 10.81 meters per second is. I have no idea how fast that is.
Sorry, his acceleration got really slow really fast.
Well, yeah, of course, but this is what happens. Your speed levels off. This is what happens when you run, unless you're like, superhuman. Unless, it's like the movies. Okay, so how many, if our delta x is 0.5, it's Simpson's rule with how many pieces? 10. So S sub 10. So we have delta x, so 0.5 over 3. Okay. Then we have 1 times, what's the first thing we have for the f? 1 times 0, right? Does it make that make sense? Or just 0? What's the first number that appears after the second term's coefficient? 4. So it'd be 4 times 4.67 plus 2 times plus 4 times 8.86, 2 times 9.73, 4 times 10.22, 2 times 10.51, 4 times 10.67, 2 times 10.76, 4 times 10.81 plus 10.81, right? When you have this many numbers, this is probably a good time to do math with friends. As in, like, you both take your calculators and you both plug them in and you make sure your answers match. Although the WebAssign makes that difficult, doesn't it? You do your friend's problem with them and double check, and then your friend does your problem with you to double check. WebAssign randomizes these numbers so you can't copy. Okay, so when you do this, we get approximately 44.735, and since it's a physical situation, give me a, units, meters, which you could just say M, M's fine. Also, be careful that the units match. So sometimes this book can be mean and tricky, and they'll give you T in seconds and give you V in like miles per hour. And then you have to convert your miles per hours into like the same units as seconds, or convert your seconds into hours. Does that make sense? Okay, it's disgusting, and if it just watch out for that. Maybe would be happening. I wouldn't intentionally do that, but it might have happened on WebAssign. Yeah. You're free to use technology to do that conversion if you'd like Google does it. So.
We never like that on a test.
No. Like this one, I'm pretty sure has that problem. I'm pretty sure it's a typo because the answer key in the textbook did it differently. So you see how it says this thing, that water leak from a tank at a rate of R of T liters per hour. So R's units are liters per hour. Notice how they labeled the other axis as seconds, and I did not, and you can't do this on your homework because like you don't know if it's a typo, but you can ask me if I think it's a typo. This probably is supposed to be hours, and I'm not sure if that's because I took a screenshot of somebody's like a picture in a textbook, and it was from a different problem or something. Okay, that might have been me. So that's supposed to be hours. Otherwise, it would be really evil. You'd have to change your liters per hour into liters per minute, so which would not be. It'd be divide everything by 60, right? It'd be not terrible, but it'd be not great. I didn't intend for it to be like that. But
So when in doubt, assume the writing of the problem is the correct writing?
Well, yeah, assume the problem is the correct writing, and when in doubt, just ask me.
Okay.
That's always the safest thing to do, is just to ask me. All right, so we get to choose. So we can choose delta x, and also like n, but remember that n must be even. So does anybody see any reason not to pick delta x equal to 1? If you pick delta x equal to 1, have we divided it into an even number of intervals? Yeah, so then let's just let delta x equals 1. Or I guess it's not delta x in this case, it's actually delta t, to be completely technical, right? Because they're t axes, but whatever. Okay, so let's make a table of our estimates, t and r of t. So if t is 0, that one's pretty easy to estimate. Your r of t is 4. When t is 1, r of t is 3. When t is 2, r of t is... I said so 2.3, right? 2 1/3, 2.3. When t is 4, or I skipped 3, I'm so sorry. When t is 3,
1.9?
yeah, sure, 1.9 is what I got. T is 4, I said 1.5, yep. T is 5, we got, my answer key used 1.1, so I'm going to go with 1.1, but I would also take 1.2, and then by 6, we're at 1. In my experience, for questions like this, WebAssign does have some tolerance for your answers being different. Like, I've seen students ask questions, and they have an answer that's not what my answer key says, but WebAssign still counts it right. I'm not sure how large that tolerance is. Does that make sense? Yes?
If we're doing a question or quiz like this, do you actually want us to make that table, or can we just start plugging in?
You can start plugging in values, and I'll just show me your work. Does that make sense?
Yep.
Yep, so like, for example, I think the question is could I just go straight to Simpson's with 6 approximations is 1/3, and I could just say, well, 1 times 4, plus 4 times 3, plus 2 times 2.3. That's what you're asking, right?
Yep.
4 times 1.9, yeah, totally, you could skip to that, no problem.
Yep.
Plus 2 times 1.5, 4 times 1.1, and then just 1. That's approximately 12.2 liters. Is that all right? Okay.
So if I get this backwards, if I do 2.
It's going to be wrong.
Yeah, it's going to be wrong.
It's going to be wrong, yep, unfortunately. Google knows, as does Wikipedia. So, like, if you forget, or your notes know, right? Those are also posted on Blackboard. So there's lots of places, and your book, you can tell that from there too, right? There's tons of places you can check this. Okay, so the last thing we're going to talk about today that's new is the error bound for Simpson's rule. So it's sort of similar-ish, right? Except for the other rules, we looked at the second derivative, right? This one we look at the fourth. The b minus a power changed to the fifth, right? The denominator became n to the fourth, which means that it will be more accurate for like smaller n's. Does that idea make sense? Because if you take like 3 to the fourth power versus 3 squared, the denominator is a lot bigger when it's 3 to the fourth versus 3 squared, right? Which means you're going to have an even less error. So we had a previous problem where we looked at 1 over x from 1 to 2, and we found that we needed 41 pieces for the trapezoid rule, right? 29 for the midpoint rule. Let's figure out how many pieces for Simpson's rule, okay? There's gonna be a lot smaller. It's kind of amazing, okay? So the first thing we need to do is we need to find the fourth derivative, which is not super, super bad in this case. So find f4 of x. Okay, so f of x was x to the negative first. F prime of x is it negative x to the negative 2. Second derivative x is 2x to the negative 3, right? Third derivative is...
Negative 6x to the negative 4th?
Yep, great. And then the fourth derivative is...
24 over x to the fifth.
24 over x to the fifth.
Negative fifth, right?
Well, over x to the fifth or 24x to the negative fifth, either way. Okay. The second thing I'm going to do is I'm going to find that k. So the absolute value of the fourth derivative, that's equal to the absolute value of 24 over x to the fifth. And remember that we're still on the interval from 1 to 2. So where is that thing going to be biggest? At 1 or 2 or somewhere in the middle? It's biggest at 1, right? Would you buy that? It still has that same general structure as the x cubed graph has, right? So this is less than or equal to 24 over 1 to the fifth, which is 24. So that's what we're going to take to be k. K is going to be 24. Okay. And so we have the absolute value, the error for Simpson's rule, less than or equal to 24 times 2 minus 1 to the fifth, right? Over 180. Do we know n this time? No. And we want that less than 0.0001. Okay, so does it make sense that's the same thing as 24 over 180? is less than 0.0001 times n to the fourth.
Oh, that would have been easy.
So you divide by 0.0001. How do you, so what is 24 over 180? I don't have a calculator on me, I'm so sorry. Divided by 0.0001. I would just like a whole number, but 1333.
Yeah.
Point.
3.
Okay. So what do you use to undo the fourth power then? Fourth root. If you have a calculator but doesn't have a fourth root button, what do you use instead? You could do square root. That actually works, but
But it's the 1 over 4.
put it to the 1 over 4. That will work for things where you can't do the root trick, but that will also work. You end up with n is bigger than or equal to 6.043. Or sorry, bigger than, not, yeah. It's bigger than. Did I do something wrong? So if you unless that 1333, you end up with n is greater than 6.043. Remember how I said you have to always round up? So n bigger than or equal to 7, but it's Simpson's rule. Must be even, yep. So n must be bigger than or equal to 8. You get almost full credit if you got everything except for that last little bit, right? So, yes. But compare that to the previous estimates. We had to use 41 for trapezoid, right? 29 for midpoint, and only 8 for this one. If you're talking about computational time like a computer's using, that's a lot better, right? Or even just button punching time for yourself. Does Mills have a question? Did you have a question? No? Okay. All right. Last one?
Does this mean we get calculators on this test?
No, it doesn't. What we'll do is, like the last example I have is one that's kind of like what will be on your test. And I'll give you how you'll do the rough estimate, like the worst case, most positive scenario, big, huge bound thing. But you should use a calculator on your take-home quiz to get like more accurate estimates. If I could only give you a calculator for like one part, I would like do that, but then it's hard to time the parts as a student. Does that make sense? And I'm not comfortable giving you calculators unless you all have the exact same one, because they do largely, like, rather large variety of different things. If you have a TI-89, it will do all your integrals for you. Like, I had one, I got it on test. I don't know what they were thinking. Like, I mean, I could show my work, but I still was able to reverse engineer every single answer if I had to, so.
You can also just like program like all the identities, you could everything.
Yeah, I know. So I mean, you can like basically teach you how to take notes. I mean, like it's just too easy to cheat. So and it's also expensive. I mean, occasionally, and it's also kind of a department policy. So I'm just following it. I mean, on some level, I'd be okay with like a really basic 4-function like arithmetic thing. But I also suck at arithmetic real bad. So like when I do your tests, I have to make sure I can do the arithmetic too, which usually keeps it not ridiculous. Because I didn't pass my times table test in the first try.
So you're just gonna give us the information we would have needed the calculator to calculate?
Let's do one, okay? Let's do one that's like that. So Simpson's rule with n equals 10 to approximate this integral, and then estimate the error, and I told you what the fourth derivative is. Okay. So first of all, delta x. 1 point. Delta x is equal to 2 minus 0 over 10, which is 0.2, or 1/5, whatever.
It's easier to use decimals here.
Whatever you want. Simpsons. So S10. 0.2, don't forget the over 3. So first we plug in 0, right? Then coefficient of 4, and we plug in 0.2, right? Does that make sense? What's the next coefficient? 2. The next coefficient's 2, and what do you plug in? 0.4. I mean, you can, there's too much list, so say plus dot dot dot. What's the second to last thing you have?
4e to the negative 1.8.
Mm-hmm, great. And the last thing you have is e to the,
Negative 2 squared.
on your test, we'll make n sufficiently small that you should list them all out. Does that make sense? Yeah.
What about the kind of second half of the equation, the 4x to the 4th minus 12x squared plus 3?
Oh, that's the fourth derivative, and we're gonna use that to estimate the error.
Oh, okay.
Does that make sense?
Yeah.
Yep, okay. So when you plug in chug and plug this in, you get approximately 0.882. Did I already do this one? I think we did.
Yeah.
Did we even use Simpson's rule? Oh, we must not have. We used the other rules, right?
Yeah.
Yeah, okay. I think the S,
Same answer?
or if it wasn't, it was quite close. Was it quite close? Okay. Okay, so let's talk about how we're gonna so we wanna estimate the error. Let's talk about how we're gonna estimate it with technology and without technology. So,
It was exactly the same.
It was exactly the same.
okay, that probably has to do with how I rounded, because I bet if I had included more decimals, they would not be the exact same. So with technology, you're gonna graph this fourth derivative on what interval? So just change the window of whatever screen you're looking at to include that only. And you're gonna see that the absolute value of that thing is less than or equal to just plugging in 0, which is, in this case, 12. So 12 will be the thing you take to be your k. And with those error estimation formulas, the hardest thing you have to do is figure out what that k is, right? The rest of it's given to you as what your a is, what your b is, what your n is, right? Okay, so here's really rough k without technology. As in like on your test, okay, for example. Absolute value of the fourth derivative. That's equal to the absolute value of 4 e to the negative x squared times 4x to the fourth plus minus, sorry, that was a typo. Minus 12x squared plus 3. Okay, so that's less than or equal to 4 e to the negative x squared. Those are positive, they can come out of the absolute value bars, right? And I think like worst case scenario, x to the fourth is positive, 12x squared is positive. So like you could just say, well, this is less than or equal to 4x to the fourth plus 12x squared plus 3. You know that's true, right? And this thing will be biggest at x equals 0. Does that make sense? This thing is going to be biggest at 0 or 2 or in the middle. At 2. So just plug those numbers in. This is less than or equal to 4 times e to the 0, 4 times 2 to the fourth, plus 12 times 2 squared plus 3. And you can take that to be your k, and if it's a test situation, all we're testing is can you get some estimate for k, so just leave it, don't simplify it, like, stop, okay? But the point is just consider like the worst possible cases for both parts of the function individually, and I'll give you a rough estimate for what k could be. That ends up being 460, which is, you know, way bigger than what we had, right? That's how I'd like you to give you an estimate without technology. So if this is a take-home quiz, what number would you use to do your error estimate? The 12 or the 460? 12. So let's plug that one in. 12 times 2 minus 0 to the fifth over 180, and it's 10 to the fourth, that's equal to 0.0002.
Technically not more accurate than the